In this video, I will walk you through free response question number 5 from the 2011 AP Calculus exam. This problem is primarily about differential equations. At the beginning of 2010, a landfill contained 1,400 tons of solid waste. The increasing function W models the total amount of solid waste stored at the landfill. Planners estimate that W will satisfy the differential equation dW dt equals 1 over 25 times W minus 300 for the next 20 years. W is measured in tons, and T is measured in years from the start of 2010. Part A. Use the line tangent to the graph of W at t equals 0 to approximate the amount of solid waste that the landfill contains at the end of the first 3 months of 2010. That's time t equals 1/4. Whenever we need to write the equation of a tangent line, we love to use point-slope form because we know all we need is a point and the slope. Because W is a function of time instead of x, we will use the variable t. For the point, we will use the point of tangency. We are told that the line is tangent to the graph of W at t equals 0. So the point of tangency is 0, something. But we are also told that at the beginning of 2010, and that's t equals 0, the landfill contained 1,400 tons of solid waste. So 0, 1,400 it is. The second derivative gives the slope at any point. To find the slope at 0, 1,400, we just need to evaluate the derivative at W equals 1,400. That turns out to be 44. So the slope of the tangent line is 44. Now that we have a point and the slope, we can easily write the equation of the tangent line. It goes y minus y, so y minus 1,400 is equal to the slope, which is 44, times t minus t, which is 0. We don't really need the minus 0 part, so now we have this. This is an acceptable equation of the tangent line, but I think it might be nice to add 1,400 to both sides of the equation. So the equation becomes y equals 44t plus 1,400. We can use the tangent line to approximate the amount of solid waste at time t equals 1/4. We just need to evaluate y at t equals 1/4. This turns out to be 1,411. At the end of the first 3 months of 2010, there are about 1,411 tons of solid waste in the landfill. Part B. Find the second derivative in terms of W. Use the second derivative to determine whether your answer in Part A is an underestimate or an overestimate of the amount of solid waste that the landfill contains at time t equals 1/4. We can find the second derivative by taking the derivative of the first derivative. I'm going to just bring down the 1 over 25, but then I take the derivative term by term. The derivative of W is dW dt, and the derivative of a constant is 0. However, we have this nice expression for dW dt right here. So instead of writing dW dt, let's replace it with this expression. This is an expression for the second derivative. We can simplify it a little bit by multiplying 1/25 times 1/25. So that's the first part of what they asked us to do. We found the second derivative in terms of W. How do we use this to figure out if our tangent line approximation from Part A was an underestimate or an overestimate? If the graph of W is concave up, a tangent line approximation will be an underestimate because the tangent line is always below the curve. W will be concave up if the second derivative is positive. If the graph of W is concave down, the tangent line approximation will be an overestimate because the tangent line is always above the curve. W will be concave down when the second derivative is negative. In the setup of the problem, we are told that there are 1,400 tons of solid waste at the beginning of 2010. That's time t equals 0. We are also told that W is an increasing function. So we're starting at 1,400 tons and it's only increasing. We just saw that for t greater than 0, W is greater than 1,400. But if W is always greater than 1,400, that means this expression is always going to be positive. In other words, the second derivative will always be positive. So that means the graph of W is always concave up. So the tangent line approximation is an underestimate. Part C. Find the particular solution W equals W of t to the differential equation dw dt equals 1 over 25 times W minus 300 with the initial condition W at 0 equals 1,400. This is a separable differential equation. So let's get all of the W's on the left and all of the T's on the right. To begin, let's move this dt to the right-hand side by multiplying both sides of the equation by dt. So now we have this, and all the t's are on the right. We want all of the w's on the left, so let's move the w minus 300 over to the left by dividing both sides of the equation by w minus 300. Now that we have all the w's on the left and the t's on the right, we can integrate both sides of the equation. We will use a mental u substitution right here on the left. Imagine that u is equal to w minus 300. We really wouldn't even write this down. In this case, u prime is going to equal 1. When you do the substitution, you always divide by u prime, but dividing by 1 changes nothing. So we can go ahead and just do the antiderivative of 1 over u. And we know that to be the natural log of the absolute value of u plus c. I will save the plus c for the right-hand side of the equation. Over here, the antiderivative of 1 over 25 is just 1 over 25 t. And there's your plus c. Because w is always greater than 300, this will always be a positive expression, so we don't need the absolute value. Let's use the initial condition to find the value of c. When t is 0, w is 1,400. Substituting 0 for t and 1,400 for w, we have this. This means c equals natural log of 1,100. Let's substitute this back into the equation right here. So far, we have this. We need to write the solution in the form w equals a function of t. So we need to get w by itself. We can make this natural log sort of go away by exponentiating both sides of the equation. In other words, we can drop a base e on both sides, making each side the exponent of the base e. Base e and natural log are inverse functions, so right here they will cancel each other out, leaving w minus 300 on the left. On the right-hand side, I'm going to use a property of exponents that says e to the a plus b is equal to e to the a times e to the b. Similarly, e to the 1/25th t plus natural log 1100 will equal e to the 1/25th t times e to the natural log 1100. I'm seeing here again I have a base e raised to a natural log. Base e and natural log are inverse functions which cancel each other out. So that's going to leave just 1100, which I'm going to put in the front. So now we have this. Finally, we just need to add 300 to both sides to get w by itself. So here is the solution to the differential equation that fits the initial condition.